Hello students, in previous lecture we have studied symbol and pin diagram of an operational amplifier IC741 and block diagram of operational amplifier. Now in today's lecture we are going to learn about important parameters of an operational amplifier. Why we have to study these important parameters of an operational amplifier? Because an operational amplifier produces certain errors which are created by internal imbalance within the op-amp circuit itself. These errors are known as offset. It denotes the existence of DC output voltage even when no signal is applied to any of the input terminals of the op-amp. The factor is drift and slew rate. All these parameters are to be considered while designing the op-amp circuit. Student, we have discussed previously what is meant by drift. Drift means this is unwanted signal, that is change in the output voltage without change in the input voltage. So this factor, slew rate, drift, all these parameters are to be considered while designing the op-amp circuits. Most of the manufacturer provides a circuit diagram, specifications, graphs and important parameters. So we have to know all these parameters before performing the practical or theoretical study of this operational amplifier. Now let's begin with the first important parameter, input bias current. It is denoted by IB. This is the average of two input currents which flow into the inverting and non-inverting terminals of an operational amplifier, and it is given by the equation IB is equal to IB plus IB minus upon 2. Generally, op-amp has differential amplifier at the input stage. The differential amplifier is a transistor circuit, all of you know that, which is a current operated device. So the two transistors are identical. Students, all of you know that the main block of this operational amplifier is nothing but differential amplifier, and that differential amplifier consists of two identical transistors. So you can see these are the two identical transistors and this is differential amplifier. Okay students? Now the current flowing through the base of the two transistors must be equal. Okay? When it is unequal, base current flows through external resistance. It produces a small difference or differential input voltage which indicates and produces an offset output voltage. The smaller bias current, better is the produces an offset voltage. Okay students? So therefore the smaller the bias current, better is the performance, because the error in output voltage can be minimized. It can be defined as with the help of this equation. It is the average of the two input current. One is from inverting and another is from non-inverting. Okay students? So we can say that it is the biasing current required at either input to provide a zero output voltage with zero input signal. Ideally, its value is 0 and practically its range is from 80 nanoampere to 500 nanoampere. Students, you will get a clear idea by using this diagram of an operational amplifier. Second one is the input offset current. It is the difference between the current into the inverting and non-inverting terminals of an op-amp. Okay students, and it is given by the equation I in is equal to I1 minus I2. Suppose this I1 is the current through the inverting while I2 is the current through the non-inverting terminal of an op-amp. It shows us the difference between these two currents. Its maximum value is about 20 nanoampere 20 nanoampere. For example, if it is 15 nanoampere, it means that we find 15 nanoampere current more in one of the base than the other. So, smaller the offset current, better is the op-amp performance. Ideally, this input offset current is 0. Now, next parameter is input offset voltage. For ideal op-amp, output should be 0 when both the inputs are grounded. But practically op-amp output is not 0 when both inputs are grounded. So, a small amount of voltage is applied the input terminals to make the output 0. This input voltage is called input offset voltage. Means this voltage is necessary to make the output voltage of an op-amp 0 when inputs are grounded. Okay, students? So, this is a applied input voltage, one of the input of an operational amplifier that causes the 0 output voltage in the operational amplifier's output. Okay, students? In this diagram, you can see one of the input is grounded and this input offset voltage is applied to the another terminal of an op-amp. Then we'll get the output voltage 0. Next is the output offset voltage. It is the output voltage of an op-amp when V1 and V2 both are 0. Then this output will be 0 and this V0 is nothing but output offset. Next, common mode rejection ratio. Students, all of you know that in differential amplifier we have discussed in detail about this common mode rejection ratio. In short, we call it CMRR. What is meant by CMRR? CMRR is nothing but the ratio of differential mode gain to the common mode gain. And tell me, what is the value of this CMRR? Yes, this is infinite. Ideally, CMRR is infinite. Practically, it is very, very high. The common mode rejection ratio may be defined as the ratio of the differential voltage gain and it is denoted by ADM in this equation, and common mode gain is denoted by letter ACM. Okay, students? In differential amplifier, we know that this ADM is nothing but differential mode gain is nothing but V0 upon V1 minus V2, and this V1 minus V2 is nothing but VD, while in common mode gain V0 upon VCM, and this VCM is equal to V1 plus V2, or simply we can say that V1 plus V1 upon 2. So simply we'll write VCM is equal to VM. VCM is equal to V1. Okay. So, as I have explained in the differential amplifier, that is CMRR, it is infinite. So, higher is the CMRR, better is the quality of an op-amp. So, ideally it is infinite, but practically it is 90 decibel. How it is? 90 decibel. Now next parameter is slew rate. Slew rate is defined as the measure of how fast the output voltage of op-amp can change with respect to the time. Means it is the change in the voltage with respect to the time, that is the maximum. So slew rate is equal to dV0 by dt maximum. So it is nothing but the response time with respect to the change in the input. Means you can see this is a time, input time, and there is a change. So you can see there is a 0.5 volt per microsecond, means response time is 1 microsecond and it is about 0.5 volt. So unit of this slew rate is, it is defined It is specified in volt per microsecond. Means here by using this diagram you can say that 0.5 volt per microsecond. In ideal op-amp slew rate is about infinite. This slew rate is the most important specification affecting AC operation. It limits the output voltage at higher frequencies. So, if sharply rising, that is overdriven signal is applied at the input of op-amp, the output gets delayed, giving rise to a delayed feedback. Therefore, distortion output is obtained. And you can see the distorted output in this way. Suppose this is the sine wave and that sine wave turns into the triangular. Okay, in this way this is a distortion. Okay students, you can see in this diagram at higher frequencies the waveform becomes triangular. Slew rate depends upon compensation technique also. So students, remember that the slew rate is defined as the dV naught by dt. So it is the ratio of change in the output voltage with respect to the time, and that time is in microsecond. Next is a drift. We have already discussed in the first point in the beginning of this chapter, that is drift, or simply we call it thermal drift because it is related to temperature. So ideal parameters VIO, IB, that is input voltage, IB is nothing but thermal current drift, and IIO are constant for op-amp but practically vary with change in temperature, change in the supply voltage VCC and VEE, and change in the time. Okay students, so the average rate of change of input offset voltage per unit change in the temperature is called as a drift. You can see all these three different equations. Thermal voltage drift is equal to delta VIO upon delta T, that is the unit of this thermal drift voltage is microvolt per Celsius. Thermal current drift, that is delta IIO, that is input offset current, upon delta T. Delta T is nothing but change in the temperature. Okay students, all of you know that, and its unit is microampere per Celsius, and thermal drift in input bias current is given by delta IB upon delta T. So all the three relations you can see at the denominator there is a delta T, means simply we can say that this drift is related to the temperature, so the name is given here thermal drift. Next is open loop gain. In the comparison points of this first topic of the chapter, that is RC amplifier, then DC amplifier, and this differential amplifier, this first open loop gain is given there in the first sentence. What it defines? It is a gain of operational amplifier with feedback, without feedback, and load. Load means load resistance. This load resistance is connected at the output of an operational amplifier. So it is the ratio of output voltage to the differential input voltage. For IC 741 in the mid band, this gain is about 10 raised to 5. This gain has no unit, therefore it is only 10 raised to the 5. But this gain is unstable and it is affected by changes in supply voltage, temperature, and aging of active devices. The open loop gain decreases due to compensating capacitor as the frequency increases. Students, you have to remember this sentence. Gain decreases here, so the frequency increases. Okay, so remember this sentence. Therefore, this simply all of you know that what is meant by gain. Gain is output upon input. If it is current gain, output current upon input current. If it is voltage gain, then output voltage upon input voltage. If it is power gain, then output power upon input power. By using that simple technique, you can write the open loop gain, that is nothing but output voltage upon input voltage. Is that clear, students? Closed loop gain. This is the most important parameter of an operational amplifier. The gain of op-amp with feedback is known as closed loop gain and it is denoted by letter ACL. Means you can easily judge that in the previous parameter, that is open loop gain, means the open loop gain is nothing but the gain without feedback. And what about closed loop gain? This is the gain with feedback. Okay, students? Gain with feedback. So the gain of an op-amp can be stabilized by connecting negative feedback between output terminal and inverting input terminal of an op-amp. We'll draw the diagram like this. Suppose this is op-amp. This is the inverting terminal of an op-amp. This is non-inverting terminal of an op-amp. If we have to apply the input, we can apply in this way. This is a feedback resistor, this is input resistor, and this is output. Dual power supply is connected here. Positive V with respect to ground, negative V with respect to ground. So this is the applied output or sample of the output again given to the inverting input. This is called as what? Closed loop gain. Okay, students? So the gain with feedback is called as a closed loop gain and it is denoted by ACL and the given by this equation AOL upon 1 plus AOL into B. All of you know that this beta is the feedback fraction. AOL is nothing but open loop gain. Gain always denoted by letter A, capital A. Okay, students? Typically, this closed loop gain may be 1000 or in between 10 raised to 3 to 10 raised to 5. Okay, students? So remember that in practical it may be asked, okay, what is meant by closed loop gain, or explain any 3 parameters of an op-amp, or in theory paper MCQ type of question may be asked what is meant by closed loop gain or what is the value of closed loop gain or closed loop gain lies in between dash dash range. Okay, students? So each and every topic from this chapter is most important. So study this chapter sincerely and watch each video, all of you, carefully and take out the notes in your notebook regularly. Now next is the frequency response of an operational amplifier. Student, you can see this graph. This is a graph of voltage gain versus the frequency. On the x-axis you can see the frequency is in the multiple of tens, 1, 10 Hz, 100 Hz, 1 kHz, 10 kHz, 100 kHz, and at last this is 1 MHz. Here the decibel gain is given 0 decibel, minus 20, 40 decibel, 60 decibel, 80 decibel. Here voltage gain starts from 1, 10, 100, 1000, 1K, 10K. Here is a 70.7K, 100K. You can see here 2 curves. This first curve is for closed loop gain. All of you know that what is meant by closed loop gain? The gain with negative feedback is called as a closed loop gain. Then next is the open loop gain. The gain without any feedback is called as a open loop gain. Means there is no feedback applied in the circuit. At that time the gain is called as a open loop gain. And the frequency is here at point A, it is denoted here FOL. OL stands for open loop and frequency F. So this is the frequency in open loop gain. In the similar way, FCL, it is a frequency in closed loop. Okay students, in this way there are different terms given in this graph and we have to see how is the response of frequency in case of this operational amplifier. This parameter is asked in the board theory exam, HSC board theory exam many times. So remember this is a most important parameters. Okay students? And very simple, if you can understand, you will write yourself without any difficulty. Okay students? So listen properly. In the given graph, frequency response curve shows the change in the voltage gain with respect to the frequency. As I have explained, FOL and FCL both are the open loop gain and closed loop gain frequencies respectively. If you observe this graph carefully, in the mid band of open loop here, voltage gain is about 10 raised to 5. Okay, here is a 10K, means it is increases 10 raised to 5. The frequency at which 70.7% of maximum gain is called cutoff frequency. Means it is the frequency FOL is called as a cutoff frequency. At this frequency, the frequency at which the gain, it is given here 70.7. Okay students, 70.7% of maximum gain. How it is maximum gain? It is about 100K, and out of that maximum gain, this is a 70.7% of the maximum gain at which the frequency, and that frequency is called as a cutoff frequency, that is FOL. The open loop cutoff frequency is about, how it is? Yes, 10 Hz. You can see here with the help of this graph. At this point, frequency is about 10 Hz and the gain is, okay, the gain is 70.7% of maximum gain and the frequency is 10 Hz. Beyond this cutoff, the voltage gain rose. Okay, voltage gain rose at 20 decibel, means it is decreases per decade. What do you mean by per decade? Change in the frequency or gain by a factor of 10 is expressed by term per decade. Is that clear? Okay students? So, beyond this cutoff, the voltage gain rolls off the rate about 20 decibel per decade. Okay? And here is a decrease in the gain, means gain decreases below this 70.7K. This decrease in the gain is due to compensating capacitor. Okay students? Now what happened about closed loop? In closed loop gain, what is meant by closed loop? That is nothing but the gain with negative feedback. This gain is stable. Here is a gain stable, but less than the open loop gain. Open loop gain is about 70.7% of the maximum gain, but this gain is less than the open loop gain. the closed loop gain, okay student, the closed loop cutoff frequency is about 1 kilohertz. See here, this is 1 kilohertz at this point. I have marked this 1 kilohertz frequency and its respected gain is about 1 kilohertz. So, beyond this frequency, the open loop and closed loop curves are common. Okay students, I repeat again, at this 70.7% of maximum gain, this FOL is called as a cutoff frequency, and that is nothing but 10 Hz. But in case of this closed loop frequency, that is cutoff frequency in closed loop, the gain, that is voltage gain, is about 1 kilohertz, and the voltage gain is about 1 kilo, and the frequency is 1 kilohertz. Okay students, so both the curves of open loop and closed loop curves are common beyond this frequency. Okay students, you can see here, this is beyond this frequency, both the curves are common. The frequency, you have to observe only this cutoff frequency for open loop and cutoff frequency for closed loop. Beyond this, both the curves are common. The frequency at which, now you have to see the next point, the frequency at which the gain is equal to 1. Okay students, remember that, don't confuse. On x-axis there is a frequency, while on the y-axis this is a voltage gain. This is the minimum scale of the voltage gain 1, and this is a maximum frequency given in the frequency range, that is 1 megahertz. So we can say that from this graph, the frequency at which voltage gain, this is a voltage gain equal to 1, and the unity is the gain. So the frequency at which voltage gain equal to 1 is called the unity gain frequency, and that is denoted by letter F unity. Okay students, so for this gain 1, F unity is equal to 1 megahertz, means at 1 megahertz the gain of this amplifier, that is operational amplifier, is 1. Simply we'll say that it is a unity gain follower. And so finally, gain bandwidth product is the product of gain and cutoff frequency. Gain is denoted by letter A, while frequency is F. If it is open loop gain, so the product will given by AOL multiplied by FOL, while in case of closed loop gain, means gain with negative feedback, it is given by ACL multiplied by FCL. Okay student, I repeat again, A is nothing but gain, F is frequency. For open loop, AOL multiplied by FOL is equals to ACL multiplied by FCL. Now let us compare ideal op-amp characteristics and practical op-amp characteristics. As previously we have seen in detail, so this chart summarized all the characteristics, that is open loop gain is infinite, practically it is 10 raised to 6. Second characteristics, input impedance for ideal op-amp, it is infinite, practically it is 1 mega ohm to 20 mega ohm. Then output impedance, this is the third characteristics, output impedance for ideal op-amp, it is 0, practically it is lies in between 50 to 75 ohm. Next, open loop bandwidth, this is also one of the most important characteristics. This is infinite for ideal op-amp, while practical op-amp has nearly equal to 1 megahertz of open loop bandwidth. Then input offset voltage for ideal op-amp, it is 0. For practical it is less than 10 millivolt. Then next, input offset current for ideal op amp it is 0. For practical op amp IC741 it is 10 nano ampere, very less. All of you know that CMRR is nothing but common mode rejection ratio. For ideal op amp it is infinite. For practical IC741 op amp it is 90 decibel. Slew rate for ideal op amp it is infinite. For practical 1 volt per microsecond. Response time of ideal op amp it is 0. Practical op amp it is 0.3 microsecond. Okay students, in this way today we have studied all the characteristics or parameters of an op amp in detail. So in this way today we have completed characteristics of ideal operational amplifier and practical operational amplifier, that is IC741. In next lecture we'll see linear applications and non-linear applications of an operational amplifier. Okay students, thank you.